So far in this course, we've been representing molecules in 2 dimensions. However, molecules do exist in 3 dimensions, and in order to capture molecules in 3 dimensions, we use what's called VSEPR. Okay, but before we can get into what that means, let's talk about the bonding capacity for each element here. So this should just be a quick review. So carbon is always going to form 4 bonds, hydrogen's always going to form 1 bond, oxygen's always going to form 2 bonds, nitrogen's going to form 3 bonds. So this is directly correlated to how many bonding electrons each element has. Now, VSEPR, that stands for valence shell electron pair repulsion. And the whole basis of VSEPR is that the electrons want to be as far away from each other as possible. Now, the reason why they want to be as far away from each other as possible is because they have similar charges, and similar charges repel. You got to remember that all electrons have a negative charge to them, and those negative charges are going to be repelling each other. Okay, so the shape is based on what is around the central atom, and there's 5 primary shapes that you need to know. So this whole table here, you need to know it. Okay, so let's just start off by highlighting it, and then we'll get into the shapes. So the first shape name is going to be linear. It's exactly what it sounds like. Everything's in a straight line. So in the diagram, you have your center atom, and we have 2 terminal atoms attached to the central atom, and there's no lone pairs on the central atom. For the next shape, this is called trigonal planar. And this shape is flat. So it's kind of like a fidget spinner. And the key characteristic of this shape is that on the center atom, there are 3 terminal atoms, but there's no lone pairs on that central atom. For the next shape, it's called tetrahedral. Let's do that. And the main qualifier for this shape is that there are 4 atoms attached to the central atom, but there's no lone pairs on that central atom. And to remember this shape, some people kind of say it looks like a camera tripod. So up here is your camera, and then down below is your tripod. You could think of it like that to remember the shape. And the reason why you want to remember this shape is because you are responsible for knowing the shape names as well as how they look. Okay. All right, with the next one here, this is called trigonal pyramidal. So these 2 pictures here, they're trying to represent the same compound. The one on the left is just showing the lone pair. Okay, whereas the one on the right is not showing the lone pair. So the key distinguisher here is that there's 1 lone pair on the center atom and then 3 terminal atoms attached to the center atom. And for this shape, it does look a bit like a pyramid. So if I draw a pyramid, okay, so here's where the terminal atoms would be, and this is where the central atom would be. For the last shape in this chart, there's 2 names for it. you get to choose which one you use. You can either call it bent or V-shaped. So the key distinguisher for this shape is that the center atom has 2 lone pairs on it, and then 2 terminal atoms. Okay, so once again, both of these pictures are representing the same compound. The picture on the left, it's just showing the lone pairs. The picture on the right does not show the lone pairs. That's the only difference. But it is the same compound. Okay, and the picture on the right, it's a little bit easier to see why we would call it V-shaped, because at least for how they've drawn it, looks like an upside down V. Okay, so this is another chart to summarize all the different shapes of VSEPR theory. So I would say this is important. I would highlight this. Okay. However, one shape is not in the Chemistry 20 programs of studies, so we're going to cross that one out. All right. So with number of electron groups, that could be referring to either bonds or lone pairs on the central atom. Okay. So the shape that they're first talking about with 2 electron groups, that's linear, and the bond angle, that's just talking about like this angle created from the 2 bonds on the center atom. The bond angle is 180 degrees. Okay, and the reason why it's 180 degrees is because that is what helps get the electrons in this bond and the electrons in that bond as far away from each other as possible. Okay, so again, that's just going back to the main idea of this theory, VSEPR, valence shell electron pair repulsion. The electrons in these 2 bonds are repelling each other, and that's why they're 180 degrees away from each other. So an example of a linear compound would be something like carbon dioxide. Okay, our next shape, that's trigonal planar, that's our flat one. So we have 3 atoms attached to the center atom, and the bond angles are 120 degrees. So do you need to know the exact bond angles? No. However, you need to be able to draw all of these shapes accurately. Okay, now the easiest thing, or the easiest way to remember, is you just try to spread out your terminal atoms and your lone pairs like an equal distance around the center atom. That's the main idea here. Okay. So some examples of trigonal planar compounds would be CH2O and BH3. For tetrahedral, okay, that's the main shape here. That's going to have 4 electron groups. So remember, electron groups can either be bonds or lone pairs. Okay, so when there's only atoms attached to the center atom, the shape is called tetrahedral. Okay, when there is 1 lone pair and 3 bonded pairs, so 3 atoms around the center atom, that would be called trigonal pyramidal. And then last but not least, when there's 2 lone pairs and 2 atoms attached to the center atom, we would call that either bent or V-shaped. Okay, so an example of a bent or V-shaped compound would be water, or H2O. An example of trigonal pyramidal would be ammonia, or NH3. And then an example of a tetrahedral shaped compound would be methane, or CH4. Okay. And actually, before I move on, one thing that I do want to explain, so this goes back to VSEPR being a way for us to represent molecules in 3-dimensional shapes. So you'll notice here that they have these dashes, and this is called a wedge, and this tells you whether this atom is either going out towards you or away from you. Okay, so a wedge, this means that the atom is coming out towards you. And the dash means that the atom's going away from you. Okay, so this atom is farther back in space because it's going away from you, whereas this atom here is closer to you because of that wedge. It means that the atom's coming out of the page towards you. Okay, so in order to represent VSEPR diagrams, you will need to use those wedges and dashes. Okay, so some examples of VSEPR shapes. So this says diatomic linear. That's the same as just linear. Diatomic is just specifying that there's only two atoms attached to the center atom. Okay, so don't worry about diatomic. I just need you to know the shape is linear. Okay, so how we would draw this is by going like this. Okay, so not all shapes require wedges and dashes. Some shapes, like linear, you can just get away with flat bonds. Right, so this bond right here, it's in the same plane as the page, so it's just flat. Okay, with V-shaped water, so that'll look like this. Okay, now the key for V-shaped is it actually needs to look like a V, or remember, we can also call this bent. It needs to look either like a V or it needs to look bent. What will not be accepted is if you draw a bent shaped like this. Nope, that's linear and that's incorrect for water because it has lone pairs. Okay, so this is not correct. Bent shape needs to look bent. Triatomic linear, again, don't worry about that. It's just meaning that there's 3 atoms involved in the entire compound. Okay, which I should have said that for diatomic linear. It just means there's 2 atoms involved in the entire compound there. Okay, so an example here, I'll just use carbon dioxide. So it'd look like that. Okay, so a linear shape, it needs to look linear. It needs to be a straight line with all of the atoms lined up. With pyramidal, they're giving us ammonia as an example. Okay, so if I wanted to represent one of the hydrogens in the same plane as the page, I'd go flat bond. Now this one, I want to say that it's coming out towards us. So I'd draw the dash, or sorry, the wedge like this, and then the dash, so this atom's going away from us, would be like so. Okay, so for trigonal pyramidal, you have 1 flat bond, 1 wedge, 1 dash, and then a lone pair on top of the center atom. For trigonal planar, that is flat, or a flat shape. So I'll just use this compound, CH2O. So how it would look like would be like a fidget spinner. So it'd be like that. Or if you wanted to draw the BH3, could look, hang on, could look like this. And you know what, I'll draw this a little bit there so that line doesn't interfere with the picture. Okay. But since trigonal planar is flat, I do not need any wedges or dashes to represent that shape. Tetrahedral, though, so this is the one that looks like a camera tripod. So 2 bonds are going to be flat, 1 bond is going to be a wedge, the other bond is going to be a dash. So for our example, which is methane, so 2 bonds are flat, 1 bond is a wedge, and the last bond is a dash. There you go. Okay, so unless you are very experienced, most of the time you can't just look at a chemical formula and just instantly know what VSEPR shape it is. You do need to go through a process in order to figure out what that VSEPR shape is. First step is going to be to draw the structure. Okay, so I would recommend first starting off with the electron dot diagram, also known as a Lewis dot diagram, and then move on to the structural diagram, and then move on to your VSEPR shape. Okay. So with that in mind, let's just draw a little chart here. So Lewis dot diagram, also known as an electron dot diagram. So we'll go like so. Oop, that didn't create a straight line. That's okay. Let's go like so. Okay. And let's see. I'll draw this line. Let's move it just a little bit. Right there, and then draw another line. Okay, good enough. So this will be our structural diagram. Oop. And this will be our VSEPR. Okay, so our Lewis dot diagram of Br3 or boron tribromide, that's going to be, so I'm gonna like skip straight to where all the bonding electrons are paired up. However, for most students, what I'd recommend first is draw the atoms by themselves, pair up the bonding electrons, and then you can get to this step. Okay, and you know what? I'll draw these in different colors so it's easier to track where the electrons are coming from. Actually, hang on. I'm going to do this a bit better. There, there, and there. Because remember, boron only has 3 orbitals, and because it's part of group 13, it only has 3 valence electrons. And there we go. Okay, so then our structural diagram, again, if it helps you to draw the circles to know where your bonds are, that's fine. So then boron, and then wherever there's a circle, that's where I'm going to stick bond. And there's no lone pairs on our center atom. Okay, now for the VSEPR shape, because our center atom only has 3 atoms attached to it, no lone pairs, that's going to be trigonal planar. Okay, so I don't need to draw any wedges or dashes because that's one of our flat shapes. I just need to very evenly space apart all of the terminal atoms around the center atom. That's the only difference for this shape. Okay, so trigonal, planar. Okay, so this is the general guide that I would use in order to figure out what the VSEPR shape is. First Lewis dot diagram, then structural diagram, then VSEPR shape. Okay, so looking at hydrogen sulfide, let's draw a little line there just to separate it. Okay, so Lewis dot diagram of this. So we have sulfur, it's group 16, 6 valence electrons. Hydrogen, right there and there. Okay, again, if you want to draw the circles around the bonding electrons, you can. Okay, now going from Lewis dot diagram to structural diagram, we're going to replace the bonding electrons with sticks. HH, make sure to draw my lone pairs on my center atom. So this is why I encourage students to draw their lone pairs on their center atoms, because it helps them to determine the VSEPR shape. So if we look at the structural diagram, okay, we got 2 atoms attached to the center atom and 2 lone pairs. That's going to be a bent shape. So because bent is one of our flat shapes, you don't need wedges, you don't need dashes. So sometimes the VSEPR shape looks exactly like the structural diagram. So I'm going to call this bent, but you could call this V-shaped. Okay, but the key thing about bent-shaped is it must look bent. Okay. Also, while we're talking about hydrogen sulfide, it's very easy for students to get mixed up with hydrogen sulfide, hydrogen sulfite, and hydrogen sulfate. Okay, so just as a quick reminder, okay, sulfide is sulfur with a 2- charge. It's an ion. Sulfite is SO3 2-, so it's one of our polyatomic ions. Sulfate is SO4 2-. Okay, so sulfate is another one of our polyatomic ions. So just watch out for that, because that's pretty confusing for students, because they all sound similar, but they refer to different ions. Okay, and I'm going to have to extend these lines here. Oop. Oh, let's go like that. Like that. And like that. Okay, so Lewis dot diagram of silicon tetrabromide. So silicon, I'm going to have to look that one up. Oh, it's part of group 14, so that means it has 4 valence electrons. So 1, 2, 3, 4. Bromide is part of group 17, so it has 7 valence electrons. So let's just draw all of these there, and I'll put in the dots later. Seven. 1, 2, 7. 7. And 7. Okay, if you want to draw the circles, you can go for that. Okay. So the structural diagram of this would be like so. But if we look at this, okay, we have our center atom. There's 4 atoms attached to the center atom. No lone pairs on the center atom. That means this is a tetrahedral shape. So this is one of our non-flat shapes, so we need the wedges and dashes. So for tetrahedral, remember there's 2 flat bonds, 1 wedge, 1 dash. So I tend to like putting my flat bonds there. However, they don't have to be your flat bonds, right? So you could have your flat bonds here. This is your wedge. This is your dash. Or you could have this as your wedge, this as your dash, and these 2 as your flat bonds. Really doesn't matter. Just so long as you have 2 flat bonds, 1 wedge, 1 dash, that's good. Okay. So just because I have this already drawn, let's just fill in my bromides. And there you have it. Oh, I realized I should have written this. Tetrahedral. Okay. With phosphorus trifluoride, let's do the same process here. So I'm gonna have to, I can go without the lines there. Okay, so Lewis dot diagram. Phosphorus is in group 15, so 1, 2, 3, 4, 5. Fluorine is in group 17, so 7 valence electrons. 1, 2, 3, 7. Okay, so these are my bonding electrons, I guess. Kind of sounds weird, but oh well. Okay, so the structural diagram for that, always draw your lone pair on your center atom. And like so. And because we have 3 atoms attached to our center atom and then a lone pair on our center atom, this is going to be trigonal pyramidal. Okay. Oop. Phosphorus, not boron. So trigonal pyramidal, that's 1 flat bond, 1 wedge, 1 dash. There you go. So let's say trigonal pyramidal. Okay, with the next one here. Oop. So oxygen, group 16, 6 valence electrons. Chlorine, group 17, 7 valence electrons. There we go. Boop, boop. So as a structural diagram, it will look like, oh, better draw the lone pairs. There we go. So this is the structural diagram. And then since this is, we have 2 lone pairs on our center atom and 2 atoms on our center atom, then this means this is going to be bent shaped. So this is one of our quote unquote flat shapes. So really doesn't change the shape. You can also call this V-shaped. I just like bent because it's very descriptive of the shape. Okay, and then oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Boop. Okay. So this is going to be like that, which is going to be, so this is a structural diagram, but our VSEPR shape is the same shape because this is going to be linear. If you wanted to get particular about it, it would be diatomic linear, but I'm happy if you just say linear. Okay, so because it's one of our flat shapes, our structural diagram looks the same as our VSEPR diagram. So I'm just going to draw one diagram here to represent both. All right. Molecular polarity. So this is related to shape for molecular compounds. So molecules are made up of charged particles, so negative electrons and positive nuclei. However, electrons are not always evenly distributed among atoms within a molecule. So if there is an equal sharing of electrons, the bond is going to be nonpolar. Okay, so you do need to know what a nonpolar covalent bond is. I'm saying it's a covalent bond because this is for a molecular compound. Covalent bonds are specifically for molecular compounds. Okay, so this is going to happen. So you're going to get nonpolar covalent bonds when the electronegativities of the atoms involved in that bond are the same. So, for example, we have hydrogen. Okay, both have an electronegativity of 2.2. So if I draw the dipole arrow, okay, each hydrogen is pulling on the electrons in this bond with equal strength in opposite directions, so they cancel out. That's why it's nonpolar. For oxygen, so that's shaped like that. Both atoms have an electronegativity of 3.4. So both oxygen atoms are pulling on the electrons in those double bonds with equal and opposite strength, or equal strength in the opposite directions. So that's why they cancel out. That's why these bonds are nonpolar covalent bonds. Now, if there is an unequal sharing of electrons, then the bond is polar. So that's important. You do need to know that. So you need to be able to distinguish polar covalent bonds and nonpolar covalent bonds. So polar covalent bonds happen when the atoms in the molecule are different, and also when they have different electronegativities. Okay, so as a result, atoms with the higher electronegativity will have a stronger attraction for the electrons that are in the bonds, and therefore will obtain a slightly negative charge because the electrons which have a negative charge are skewed slightly towards the side of the compound that has a more electronegative atom in it. So for example, water. Okay, so I'm drawing this as the VSEPR shape. Okay, so oxygen has an electronegativity of 3.4. Each of these hydrogens have an electronegativity of 2.2. So now we're looking at each individual bond. So let's look at this bond here. The bond dipole would be like this. Same for this other oxygen to hydrogen bond. The bond dipole would be like this. So this is trying to represent that the electrons are skewed in both bonds towards the oxygen because oxygen has a higher electronegativity. Okay, so because of this, we can say that the resultant vector would be going up kind of towards the side that has oxygen in this compound. Okay. So note, not all molecules with polar bonds are dipoles because polar bonds can cancel each other out. So how you determine if a molecule is polar versus nonpolar is you need to look at the shape of the molecule. So that's why knowing VSEPR and knowing how the shapes looks are important. That's why knowing VSEPR shapes is important, because it helps you to determine whether something is polar versus nonpolar. Okay, so if a molecule is symmetrical, okay, so basically no matter how you cut it, you're going to have the same thing on both sides, then your molecule will be nonpolar. If your compound is asymmetrical, so no matter how you chop it, you don't necessarily have the same thing on both sides, that would be asymmetrical. So if you have an asymmetrical compound, then it's going to be polar. So for example, carbon dioxide looks like this. It's a linear compound. So the bond dipoles, oxygen is more electronegative than carbon. Okay, so even though carbon dioxide is made up of polar bonds, okay, because each of the oxygens on opposite ends of the molecule are pulling with equal but opposite force, these are going to cancel each other out. Therefore, this is nonpolar. So let's write out what I just said. Okay. And you know what? I'm going to move these to just below here, just to prove my point. So they're pulling with equal strength in opposite directions. Therefore, they cancel out. So this compound is nonpolar. If you wanted to use the reasoning of symmetrical versus asymmetrical, if I chopped this compound in half this way, you would have the same thing on this side as this side. Okay, so it's symmetrical that way. Alternatively, if I chopped this compound like so, I would still have the same thing on both sides. So this compound is symmetrical. Okay. So for determining polarity, this is a pretty good flow chart. So step 1, draw the structural shape. And from there, I would actually go to the VSEPR shape. So let's change this and say VSEPR. Okay, because that's a bit more accurate. So if it's asymmetrical, so for example, if you have something that is V-shaped or trigonal pyramidal, then it's going to be polar. But if you have a symmetrical shape, so something that's linear, tetrahedral, no, let's make that clear. Trigonal planar, so long as all of the atoms in all of these shapes here are the exact same, then it will be symmetrical. Okay, so breaking this down, if bonded to only one kind of atom, it's going to be nonpolar. However, if there's different types of terminal atoms, it's going to be polar. Okay, so this is a really great flow chart here. Okay. So with water, we've kind of already done this, so I'm going to speed through it. Okay, so oxygen's more electronegative than hydrogen. And I'm going to draw the lone pairs there. So because in both of the bonds the electrons are going up towards oxygen, the resultant vector would be up. Okay? Now, if you wanted to go with symmetrical versus asymmetrical, well, if you chop it like this, yeah, there's the same thing on both sides. However, if you chop this compound like this, you don't have the exact same thing on both sides of this line. Therefore, it's asymmetrical. With methane or CH4, I'm going to skip straight to the VSEPR shape. So 2 flat bonds, 1 wedge, 1 dash. Okay, so this one is a bit harder to tell if it's symmetrical or asymmetrical, but this is why I listed tetrahedral up here to help you out. So it is a tetrahedral shape because there's 4 terminal atoms bonded to the center atom. There's no lone pairs on that center atom. So then we know it's nonpolar. Typically, when you have carbon-containing compounds, if there's only one other element besides carbon, it's going to be nonpolar. Okay, but if we draw the bond dipoles, carbon's more electronegative than hydrogen. So all of these cancel out. So this is going to be nonpolar. And I just realized I didn't write polar for water, so let's write that in. Okay. Now for this one, so CH3Cl, that's going to be, so I'm just skipping straight to the VSEPR diagram. Keep in mind for students, I wouldn't be expecting you guys to instantly know what the VSEPR shape is just by looking at the chemical formula. In order to do that, you can draw the Lewis dot diagram, structural diagram, and then VSEPR shape. Okay, so the 3 hydrogens, they can go anywhere. Okay, so I could put hydrogens here and then my chlorine there, or I could put my chlorine, over here and that hydrogen over here. Doesn't really matter. It's all the same thing. You still have 3 hydrogens and 1 chlorine. Okay, so with this, chlorine is more electronegative than carbon. Carbon's more electronegative than hydrogen. Okay, but overall, okay, this compound, since it's a tetrahedral shape, but there's not all the same terminal atom, that means that this is going to be a polar compound, and the resultant vector is going to go towards the left, towards the side that has the chlorine on it. Okay, so summary of polarity. This is just summarizing everything that we've talked about. Okay, but if you follow this flowchart, you should be good. Okay. So as a helpful hint, compounds containing carbon and only one kind of atom are always going to be nonpolar. So this is what I was talking about before. So if you have carbon and only one other thing, it will be nonpolar. Okay. If you have carbon with 2 other elements, 2 or more other elements, for Chem 20, we can say it's going to be polar. So that is very important, because sometimes carbon-containing compounds can get tricky.